So the force on, we'll just say 1 from 2, would be current 1 L cross B2. So this is the force on wire carrying current 1 from the wire carrying current 2. And so it's the current 1, and that's the magnetic field created by 2. So let's go ahead and assume perpendicular that these two currents are running parallel to each other. So we'll just say I1, I2 are parallel or anti-parallel. Ultimately, that's going to make the cross product here is my vector L, or I and B, to be perpendicular to each other. And so this just becomes ILB 2. At this point, I've gotten rid of my vector aspect, so that's the magnitude of F. So that's I1L times U naught I2 over 2 pi R. So in this case, R is the radius of my Gaussian, my Amperian loop. It's how far I am from the wire. Or in this context, it's the distance between the two wires. So if I put the distance between the two wires as D, then that becomes a D on the bottom there. So what I'm left with now is mu naught I1, I2 over 2 pi D times R. And the R is separated times L. Off. Pardon?
I was thinking the D stood for diameter for a second.
Oh, sorry. D is the distance between the two wires. L is the length of the wires.
Yeah.
It's the part of the wire that's parallel to each other. And so traditionally, if I have an infinitely long wire, then I've got an infinite amount of force. Doesn't really help us a whole lot, because it doesn't tell us about how much force is going to be pushing on one particular part. So typically, this formula is expressed as in force per length to be mu naught I1, I2 over 2 pi times the distance between the wires. Because if I have infinitely long wires and each wire is exerting a force on the other one, that makes sense that it would be an infinite amount of force. So in this particular example that I had done right there, L would be the length from basically where they came into parallel to each other down to the bottom. That would be the length of L. Or in the lab, L sub P for parallel length. Let's run through a quick plug and chug. So I have a 2 ampere and a 4 ampere currents. Running parallel for 3 meters. The wires are 1 centimeter apart. What's the magnitude of the force that is exerted on either of them? Now the direction of the force you can think through using a right hand rule, but plug and chug. So we have mu naught over 2 pi. What is the value of mu naught in SI units? There's an exact way to express it. Of course, it involves pi, so is that an exact thing or not? Well, I guess pi is an exact number.
4 pi times 10 to the negative 7.
That's the one. So this is 4 pi times 10 to the negative 7 Tesla meters per ampere times I1, which is 2 amps, times I2, which is 4 amps. Or if you're feeling a little bit saucy, 4 amps and 2 amps, divided by 2 pi times the distance between them, 0.01 meters. Well, conveniently, we have some stuff that cancels out. Pi goes away, 2 goes to that twice. So I'm left with 2 times 2 times 4, which is 16. Times 10 to the, that's a negative 7, but we're dividing by 0.01, so that becomes 10 to the negative 5th. Or 1.6 times 10 to the negative 5th, sorry, negative 4th units.
Newtons per meter? Or you just need it
Oh,
in space?
I did not take that. F over L, thank you, newtons per meter. Now they're paralleling each other for 3 meters, and so we can figure out what the total force is by, that's equal to the force divided by the length, which is 3 meters. So the total force is 4.8 times 10 to the negative 4th newtons. So it's not a whole lot of force, even though these are huge currents right here, and that's a pretty long length there. But 1 centimeter apart, we probably can do better, pointing to where that, in theory, where it used to be. All right. Questions? All right, we're now ready to tackle the loop in the magnetic field. We looked at torque of it was a dipole in an electric field. We're now going to look at torque of a current carrying wire in a magnetic field. Skip that part. We have a rectangle of wire here, dimensions A times B. Let's have the current flow clockwise. Now I have a magnetic field. A uniform magnetic field, just because we can. Going to the right. So first let's just go through and figure out what are the forces acting on each segment of current. And I know I've drawn it badly here. Actually, I'm gonna just redraw that one. It's supposed to be a rectangle and not whatever monstrosity I just drew. So on the left wire, right here, what is the direction of the force acting on the left wire? Current's going up, magnetic field's going off to the right.
Into the board.
All right, so we got L cross B, yep, into the board.
Do that again?
All right, so the direction of the current flow is that up. So hand starts in that direction. So somewhere like that, and then my fingers are gonna bend towards the magnetic field, which is going this way. Thumb points in towards the board.
Oh.
So this will be the forces into the board. The top. What is the direction of the force on top?
There is none.
Why?
Because it's a cross product, if you have, if the parallel cross product is 0.
Absolutely. There is no force on the top. What about down here?
Oh,
Did you get it?
out, so it goes down. Oh.
Yep. So the current's flowing down, magnetic field's going that way, thumb points out. All this force left and force right. And then on the bottom,
No force again.
because they're anti-parallel. I can't remember if I wrote it up last time, so if I have, we'll just take B is equal to I L cross B. No, sorry, that's force. If I'm looking at a magnitude here, that'd be ILB times the sine of the angle between my two vectors here. And so in the last case, the current's going off to the left, L is in, that's my L vector right there, B is in the other direction. The angle between them is 180 degrees, or pi if you're cool, and the sine would be 0. All right, so I have this wire here where the right side is being forced out, the left side is being pushed in. In essence, we have a torque. Rotating about some central axis. So let's take a look at the torque. The torque of the wire will be the torque from the left side plus the torque from the right side. Total torque is always sum of torques. What's the formula for torque?
L cross D.
Say it again?
Is it L cross D?
No, not L cross B. In general, formula for torque, not in this specific case.
Length
FD?
times force, or, yeah,
Sorry.
FD? No.
F cross R,
By the way,
R cross F.
R cross F.
yeah.
Okay.
FD works if you have to be very specific of, that is if the moment arm is perpendicular to the force and you don't care about direction. So this is my axis of rotation right here. In my first case here, for my left, R is a vector to the left. So let's establish a coordinate system here. So I hat to the right, J hat up, and then K hat out. So this R, so this would be negative A over 2 I hat. That's my R there. Cross my force, which is I times the length of that, which is B, little b, times big B, and it's 90 degrees, so the sine of 90 degrees is 1. And then L, okay, and the force is outwards, the force is into the board, which is the negative K hat direction, so negative K hat. See if I can draw that a little less bad. So that is the torque on the left side caused by the force on the left side. Now the right side. Plus, what's R hat? What's, not R hat, what's my R vector now? What's my moment arm?
moving over to.
And the rest of it?
I have,
Yep. And my force is now out of the board. So that will be positive. I, little b, big B, K hat. Now down to multiplication here. What is I cross K?
J.
I cross K is, did you say K?
J.
J. Why?
I think you just use the right-hand rule to be like, when you,
there's not any more coordinates left.
I is that way. K is that way.
Should be negative J then.
Negative J. I, K is going out, so I cross K, negative J. So this becomes negative J hat. Those negatives will cancel out, so I'm left with I, A, B, big B, over 2. We have I cross K again, so it better be negative J hat. I, little a, little b, big B, over 2. Which is negative J hat, I, A, B, big B. We're about to take another step. Any questions up to here, though? All right, so we did this for this very specific situation here, but I'm going to generalize it. This little a times little b, what is that?
there,
So this becomes IA, B, negative J hat. This I times A has a special name. And they use the letter mu. This is not permeability. This is a different mu. This mu right here is the magnetic dipole moment. We dealt with electric dipole moment in the earlier chapter. Now it's the magnetic version. If the direction of mu of this magnetic dipole moment is a vector, just like the electric dipole moment was, if this vector is pointed in the direction of the magnetic field in the center, which would be into the board, find mu with the vector symbol, magnetic dipole moment, direction equals direction of magnetic field in center of loop from the current in the loop. And I threw in that last bit there because this is the magnetic field that's created because there is a current that's flowing around in the circuit. And so my torque can now be generalized. Okay. So we have mu that's going into the board. So mu is in the negative k hat direction in this case. B is in the I direction. So mu cross B. Let's make sure. So we have current flowing clockwise, which puts the magnetic moment, dipole moment into the board, and then mu cross B, negative J. All right, that works. mu. What a fun time this is. So let's think about this. We got mu sub naught, which is the permeability of free space. We have regular old mu, which is the permeability of some medium, of a medium. We have mu with a vector symbol over it, which is the magnetic dipole moment. And then we have the mu without a vector symbol over it, which is the magnitude of mu with a vector symbol over it. Now, it would be really nice, because at least coefficient of friction has the courtesy of being in a separate course. But we got these two things, which are both associated with magnetic fields, both using the same symbol. There's also, because it keeps showing up, the prefix. 10 to the negative sixth. This is all part of the glory that it's 252, where we've run out of letters, so let's just start repeating it way too much. I guess the closest that we get in 251 is the letter M can be used for probably more than we want it to be.
Did they really run out of letters?
There are only 100 letters. If you look at Greek or Cyrillic and Latin alphabets, uppercase, lowercase, we have 100 letters.
I feel like I always see the same, like 5 to 10 ones, like sigma.
Yeah, I mean, where's epsilon when you need it?
Right?
At some point, physicists started reserving Greek letters to represent particle names. So there's an epsilon particle. Oh, let's not forget a positive muon, a negative muon, generic muon.